Hello dear students. Now we will move on to section 2.7. It is about conservation laws and shock waves. Now in this section we will mainly deal with an equation called the Euler equation. It is given by ux plus uy equal to 0. Now this equation is very important as we consider its physical application. It is a very important equation in hydrodynamics. And here U represent the flow of mass with concentration U, and the speed and we are assuming that the speed of the flow depends on the concentration U. The term y usually represent time. In some texts you can see here ut instead of y. Okay, dou u by dou t. So t represent time and x is a spatial variable. Now this models the phenomena of flow of mass with a concentration u. So this has got much physical application. That's why many mathematicians have tried to study to get its solution. Now the thing is that you will always, we may not get a smooth solution for this equation, and in this section we will see how to extend our problem when the solution is not smooth. The solution may develop some type of singularity which are also called shock waves. Now, what are these shock waves? How to deal in such cases where the solution is not smooth? It will have some discontinuities will be there in the solution and some shock waves will be developed in the solution. So how to extend our problem in such cases, that we will deal here. So this equation is mainly known as the Euler equation. So before directly going into the Euler equation, we will see its simplified form where u is a constant. Okay, we had ux plus uy equal to 0. Now first suppose that u is constant, let u equal to c. So this becomes a linear equation. This equation is also called a transport equation. So here y represent time. Okay, so this is cux plus uy equal to 0. Here c is a constant. It usually represents the speed of the flow. And suppose the initial condition is u at x0 equal to h of x. Now as usual we will write the characteristic equation. So xt, characteristic equation, xt is coefficient of ux, so it is equal to c. Yt, coefficient of uy, so it is 1, and ut is 0 here. Initial condition, x at 0s is s, y at 0s is equal to 0. Okay, here you have to write 0. Okay, this is missing here. So y at 0s is equal to 0 because y is 0. And u at 0s is equal to h of s. Now as usual we can solve the characteristic equation to get the characteristic curves. So here we have xt equal to c. This is dx by dt equal to c. So dx equal to c dt. Integrating you will get x equal to ct plus f1 of s. Now when you apply the initial condition as we did in the last section, when t is 0 we will get x is s. So f1 of s is s. So you will get x equal to ct plus s. So this I have directly written the characteristic curves here. I have integrated this and applied the initial condition. Similarly, dy by dt equal to 1. So dy equal to dt, y equal to t plus f2 of s. When I apply the initial condition, I will get f2 of s equal to 0 because y of 0s is 0. So y is t only, y equal to t. Third one is ut equal to 0, which implies that u must be a constant. U is a constant, but at t equal to 0, u takes the value h of s. Hence that constant must be h of s. So we will get u equal to h of s. So we have the solution u equal to h of s, and what is s? S we can get it from here. We are inverting the transformation. Okay. So s is x minus ct and t is y. So you will get s equal to x minus cy, u of xy equal to h of x minus cy. Okay, so this is the required solution, u of xy equal to h of x minus cy. It means that u is a constant along these characteristic curves. Okay, along these curves u is a constant. So u lies here. So when x equal to, we have x is 0, u is a constant, and these are the characteristic curve. X minus cy equal to s. When suppose s is here, then you will have a line like this, the equation of a line. Okay, x minus cy. If s is here, you will get a line like this. So all this characteristic line like this. And u is a function of x minus cy. So you will get, so in this way we can see that there is no problem in solving the linear case. So we have seen how to get the solution of the transport equation. It is quite easy. Now next we will move on to, so here in this problem we say that the initial shape does not change. The wave moves with speed c along the x-axis. Okay, as s increases, here you have a speed curves like this. So the initial shape is not changed because u is a constant that is carried here. Now we consider our Euler's equation. So it is a quasi-linear equation, uy plus ux equal to 0 with the initial condition u at x0 equal to h of x. So again we will write the characteristic equation and initial condition. So we have xt equal to u, yt equal to 1, ut equal to 0. Initial condition, x at 0s is equal to s, y at 0s equal to 0, u at 0s equal to h of s. Now we have to solve the characteristic equations to get the characteristic curves. Now xt equal to u, you cannot directly do integration here. So we will do one more times differentiation. So this becomes xtt equal to ut, and ut is 0. So we have xtt equal to 0. So this is a second order ordinary differential equation with constant coefficient. Its auxiliary equation is m square equal to 0. So the roots are 0, 0. 0 is a double root. So we can write the solution x as some constant. Constant is a function of s that we have already studied. Okay. So I can write x as f1 of s plus f2 of s t. This is just like c1 plus c2 t. Okay. Now I will apply, so from here I have u. What is u here? U is xt. Xt is u. So I got x, now I can find u. U is derivative of x with respect to t. So when I differentiate it with respect to t, I am getting f2 of s. So u is f2 of s. Now apply the initial condition. So x at 0 is equal to s. So when I put t equal to 0, this term vanishes and I will get f1 equal to s. So I have x is equal to s plus f2 of st. Now apply the condition, initial condition to u. U at 0 is equal to h of s. It implies that f2 of s is h of s. Therefore, we substitute the value of f1 and f2. So we get this characteristic curves as x equal to s plus h of st and u is equal to h of s. And y we can do direct integration because yt is 1. So y we will get t. Okay, if you apply the initial condition, you can see that this function should be 0. So after applying initial condition, I will get y equal to t. So these are our characteristic curve. X equal to s plus h of st, y equal to t, u equal to h of s. Now I will try to express u as a function of x and y. So what is s here? From the first equation, s is x minus h of st and h of s is u. So x minus uy. So our function u, y is t. Okay. So our function u becomes u equal to h of s, and what is s? S is x minus uy. So I got u as a function of x minus uy. You can see that in RHS also u is there. In LHS also u is there. So I'm unable to write u in an explicit form as a function of x and y. So here we got an implicit form. Okay, because in LHS and RHS both u is there. If I can write u as a function of x, y alone, then it is a explicit form. So here we are getting solution in the implicit way. U is a function of x minus uy. Okay. Now to study the nature of the characteristic curves, we will see the projection. So when you see the projection of the characteristic curves, what we are getting is y is t. So we have x is equal to s plus h of s y. Okay. And we have u equal to h of s. So this is a constant. Now it means that u preserves the initial value along the characteristics. And the characteristics are straight line, because when you fix if you fix s, you can see that these are the equation of straight line. So characteristics are straight line and u is a function of these straight lines. Now we will see some other phenomena also here. We have u is a function of u is equal to h of x minus uy. Now what is ux here? From this I have ux is h dash of x minus y into derivative of this. So I will get 1 minus derivative of u with respect to x, ux y. So from this I can write what is ux. Okay, so ux by h dash is 1 minus uxy. I have taken ux common outside. So I will get 1 by h dash plus y equal to 1. I have taken LCM here and taken this to RHS. So I get ux equal to h dash by 1 plus h dash y. So it means that the solution, u is a solution. Okay, so the solution's derivative ux will blow up if the denominator vanishes. Ux does not exist if the denominator vanishes. It happens at the point when 1 plus h dash of y equal to 0. That is, at that point y is minus 1 by, if 1 plus h dash of y equal to 0, then y becomes minus 1 by h dash of x minus uy, and x minus uy is s. So it is minus 1 by h dash of s. So at this point the solution will the derivative will blow up. That is, the derivative does not exist, so the function is not smooth. Its partial derivative does not exist. So actually we have already told that y denotes time here. Okay. Now if h dash of s is negative, you will get y as positive. Since y represents time, it should be positive. Okay. So this time is called the critical time. So up to this critical time, we will get a solution. Now after this critical time, what happens is the solution will the derivative will blow up. That is, the derivative does not exist. So the solution loses its smoothness. The solution will not be further smooth. It may have discontinuities. Okay, so after this time is called the critical time. We will denote it by yc. So y critical, yc is denoted as minus 1 by h dash of s. And our time should be positive. So it means that this h dash of s should be negative. Okay, it means that h should be a decreasing function. We know that if h is a decreasing function, h dash of s is less than 0. Okay, so if h dash of s is less than 0 for at least one s, then at that point we have h is decreasing. So if h is never decreasing, then we will not have any singularity. Okay, so if y is less than this critical point, so the critical time is that time after which the solution loses its smoothness and the solution may have discontinuities. If y is less than yc, for y less than yc, there is no problem, we will have a smooth solution. Because since we are these are the smooth solutions of the PDE are also called the classical solution. Okay, the classical solution will be continuous differentiable and they will be satisfying. So the PDE, they are the solutions, also they are differentiable. But you can see that if y is greater than yc, then the smoothness is lost. And in such conditions, in such situations, we will not further get a smooth solution for the PDE. Now we have to study the behavior of the flow of this mass when y is greater than yc also. Okay, after the critical, because the liquid is flowing. Mathematically we are getting a problem, but the liquid is flowing without any problem. But mathematically, how can we justify it? How can we extend our problem to the region where y is greater than the critical time, where smoothness is lost or where there are discontinuities? So that is the extended problem, and we denote such solution that we are extending to the portion where the solution is not smooth is called weak solution. It is called the weak formulation of the PDE. Okay, so one we have classical solution, another we have weak solution. Classical solution means at that time the derivatives will be smooth, the solution will satisfy the PDE, it will be continuous and differentiable, there will be no problem for the smoothness. But we see that after the critical time, when y is less than yc, we have a smooth solution, we have a classical solution. When y is greater than the critical time, we see that the derivative blow up and hence there are discontinuities. And our problem is how to find solution in that condition when y is greater than yc. Such solutions are called the weak solution, and to formulate the problem, the formulation of the PDE is called the weak formulation of the PDE. In such cases, we will use integral form of the differentials, because when we write in the derivative form, it should be differentiable. Okay, it should be smooth function. But for integrals, that is not required. So here we will seek the help of the integral form, and we will find the solution in terms of the integral form. So that is called the weak formulation of the PDE, which we will study in the next section. And you can see that here I have written if y is greater than yc, that is after the critical time, the classical solution is not defined. Okay, so the necessary condition for singularity formation is that h dash of s is less than 0. That is, if h dash of s less than 0, then this become negative, so y become positive. Y is time, so it should be positive. So it means and in turn we know that h dash of s less than 0 implies that h is a decreasing function. Now if h is never decreasing, there will not be any singularity. But practically it never happens. In real world problem it never happens. We always get a singularity. Okay. So the first time when y satisfies the equation 1, then the solution will become singular, and that value of s for which this vanishes or this becomes singular. Okay. 1 plus h dash of y equal to 0, this vanishes, or we have this value, y takes this value. That value is obtained when h is minimal. It happens for the minimal value of h dash of s. Okay. Now we will extend our solution beyond this critical time, that is critical time is yc. We will see how to write the solution when y greater than yc. At y equal to yc, there is a breakdown and the classical solution does not exist. So we will go for a weak formulation. Okay. Now in this case, the PDE will have non-smooth solutions which are not differentiable. A solution of the new extended problem is called a weak solution. Such solutions are called weak solution, and the problem is called the weak formulation of the PDE. Okay, so in the next section we will see how to do the weak formulation of the PDE. That is, when y is less than yc, there is no problem, we have a classical solution. When y is greater than yc, there is a discontinuities will be present in the solution and the classical solution does not hold, and we have to go for some other method. That is, we will find a solution using integrals, and that is called the weak formulation of the PDE. That we will discuss in the next class. Okay.